let's look at the results from our fun and exciting card sorting experiment. For those of you who actually did it, glare. Uh, let's see, like Mr. Zapala, did you put in your last piece of data? Uh-huh. Mm. I mean, it was probably, yes, the anonymous frog or Frumius Bandersnatch. Yeah, I deleted all of those. So anyway, okay, so let's look at the results of this. So I changed a little bit of the computation down here at the bottom. The other thing, of course, is that you'll notice there's a whole lot more rows than when you guys were doing this because we also have the other class. Their data is in here also. So I computed the averages here for each trial. And then this number here is the average over all trials. So I averaged literally every attempt, all three attempts for sorting a single card or single suit, and then so on for the other ones. So the numbers that are to the left and to the right are the minimum and the maximum that occurred within the within that set of trials. So the minimum that anybody was able to sort the one suit set out of the entire both classes was 13 seconds. The maximum was 53 seconds. All right, now why, and the average was 20. Okay, so what possibly explains the discrepancies between the mins and the maxes other than slow sorting? Huh?
The way you shuffle could affect it. Like there could still be a few cards still in sequence if you didn't do it super thoroughly.
Right. Okay. So the shuffling job, because even if you were a perfect shuffler, there is a chance that you shuffle them and they're all in exactly the correct order. Right. Now it's not a very big chance of that occurring, but it could theoretically happen. Okay. The other thing, as Thomas said, is the exact sorting method, which I never actually told you guys how to sort them, like the actual what you do in terms of moving cards or whatever. That we'll actually start look at today. One method of sort of, if you will, programming. So I just told you guys sort them, and you all picked. You just did it, right? But I never told you the actual method to sort them. I told you what the result should be, right? But the algorithm or whatever you guys used could have varied from person to person. This is one reason why having basically 45 data points is good, because we can sort of wash out that individual variation. Okay, so we've got the, like I said, the min, the average, and the max. And then over here, we've got the min, the average, and the max, and so on for the 2-suit, 3-suit, and 4-suit attempts. Okay, good. All right, so all I did was I copied those numbers over here, or actually I put in a reference so that when I put this in, you guys were still updating the numbers, that the numbers here would update, and then therefore the graph that I based off of it would also update. Okay, so let me blow up this graph a little bit so it's a little easier to see. Okay, and so what I did was I graphed, well, we had 1, 2, 3, or 4 suits. I could have done 13, 26, and so on, just counted the number of cards instead, but whatever. Okay, and I've got the minimum numbers for each type of sorting, the averages for each type, and the maximum numbers for each type. And I've graphed those here on this table. Okay, or there are 3 lines here. So let me actually edit this for a second to, if Sheets will cooperate with me this morning. Oh, there it goes. Okay. All right, let me turn off the trend lines for a second. I'll put them back on in a moment. Okay, so here's the curves that we see. Now, the maximum curve is kind of janky, as you can see. But the minimum and the average curve look a little bit more like what I was expecting to see. Okay, first off, are those straight lines? No. Okay, and certainly not the maximum one because, well, yeah. They're not straight lines. Okay, and I knew that they weren't going to be straight lines. Um, because I mean we talked about it, right? Doubling the number of cards more than doubled the time it took, sort of on average, to do this. Okay, so we wouldn't expect that there's a linear function that fits that describes this sorting pattern. But looking at it, and it's maybe not so great easy to see, but like looking at say the blue one, what kind of curve maybe jumps out at you as being a good fit to that? Okay, exponential possibly, or okay. So when you say exponential, what do you mean? Do you mean like an e to the x or like an x squared? Like what sense to exponential do you? Okay, so e to the x, so true exponential. Um, okay, so it could look like that. What else could it look like? Well, what about like a quadratic, like an x squared kind of thing? Yeah, maybe. Okay, now as it turns out, x squared or a quadratic curve is the correct one here. And so let's put in and have Sheets do the curves of best fit. So I can do that by going to series, apply to all series because I want to do a curve line for all of them. Okay, and then I want to do a trend line, and I've chosen this sort of obnoxious pink color just to make it a little easier to see. I also want to show the R squared values, and those of you in the sciences or behavioral science, right, are used to thinking about R squared values. What does the R squared value kind of roughly speaking tell me if I've got a curve to fit some data? Yeah, how well it fits the data. Okay, and so what sort of what are good values of R squareds that you would hope to see? Yeah, 95.95 or above is usually the threshold for sort of supposing statistical significance. Um, and if you look, right, for our min and our average, we've got basically about that 95. Well, actually, for the average, we have 99%, right? And so for our average, which of course is the one in the middle, um, we've got a very, very good curve fit here for a quadratic function. For the minimum, it's still a pretty good fit. It's only 95.95 on the R squared, but that's still, pretty acceptable. And then the max one, okay, yeah, that one got a little weird. It's only 0.91. And um, so the max here, right? Why do you think maybe that this could have happened? That we got this weird crook, right? And keep in mind, this is the maximum out of the entire class and the other class for each of the three trials of sorting. What in this case, however many suits, but the weird number here is the 3-suit case. All right, why do you think that could have ended up being so? That the data is weird looking. Yeah. Yeah, it's a single person. Okay, Thomas, what were you going to say? Versus what happened when we went from 2 to 3 suits. So when we went from 2 suits to 3 suits, the 2 suits were of different colors. Suddenly, when we went to the 3 suits, now we have a suit of, there's 2 suits of the same color, right? Regardless of which colors, it's going to be one of the two, right? So in some sense, perhaps going from 2 to 3 was more complex than just going from 2 to 3, and that maximum being sort of bumped up a little bit is a reflection of that for somebody, right? Um, okay. The other thing is, how do we know that there's not sort of like a bad measurement here, in the sense of, um, I don't know, like maybe you were doing it and your phone buzzed because you were getting a bunch of upvotes on Yik Yak, and you looked over at your phone and that distracted you for 15 seconds, and then you went back to sort, but you forgot to subtract out the right, so that your measurement time was not correct. That's also a possible explanation. Now, what I have not done, and of course I could go sort through it and find who had the maximum, and then like we could like tie them to a chair and grill them for information as to why they were so slow. Um, so no, huh? Probably in the other section. Yeah. Okay. We'll blame them, right? But the other two trend lines are pretty good. Okay. And as it turns out, like this is to some extent putting the cart before the horse. I know that the quadratic is the right curve for this because reasons. And those reasons are basically the rest of today and Friday's sort of discussion. Okay. Is why I knew in advance what kind of results we were going to get, no matter how hard you guys tried to screw it up. Okay. Blake. Yeah. Okay, so let's actually talk then the algorithm, or an algorithm for sorting the cards. Okay, so what I'm going to do is, let's see if this will work correctly. I'm going to switch to the webcam, which of course is not wanting to work. Okay, I'm going to then pop this out. Windowed projector. Okay, and let me move the keyboard and move this. Okay, so let's talk actually an algorithm for sorting. Um, so I've got here some of the cards. I just picked the spades, but it doesn't really matter. And so let me just take, say, a few of them here. And um, I'm not going to attempt to shuffle particularly well. I'll just kind of do I can't do the bridge shuffle, unfortunately. I just never have been able to master that. Um, it's kind of like, like a cigarette lighter with the little rotaty thing. I mean, I don't smoke, but even just using that to light like a candle, I can't use a cigarette lighter. I just can't do it. Yeah, I guess it's a good thing I don't smoke, right? Because I'd have to walk around with like a barbecue lighter, right? Hey, man, you got a light? Yeah. Okay. All right. So let's see what we got here. And let me kind of get them into view. Okay. So got some arrangement. Okay. Whatever. Uh, Now, when you guys sorted them, I think just watching you, what most of you did was you did not lay all the cards out and then start moving cards. Okay. What it seemed like most of you did, even with the 3 or 4 suits, is you had your cards like this, and you said, I've got the 10 of whatevers, okay, 10 of spades. And so let's say that I'm going to put the spades here and the hearts here and the diamonds over there. And then you kind of say, well, 10 is like roughly 2/3 of the way through the suit. So I'll put it kind of 2/3 the way along the line. And then the 9, okay, well, that goes right next to it, and so on, right? It seemed like just watching you guys, that's roughly speaking what you did. Okay, did anybody actually lay out all of the cards before you sorted them. Okay. Mr. Sparkles did. Okay, good. That's fine. What did you do once you laid them all out, right? So I laid them all out like this. Then what did you do?
I looked for like two, and then put them into there. Put the three and put it on top.
Okay, so you kind of basically went through and searched the entire uh, pile for the two, and then searched what was left for the three, and so on. Okay, that is a perfectly reasonable way to do it. And essentially, what you did was you turned your sorting problem into a searching problem. Okay. Now, let's think about why n squared is going to make sense here, and I'll elaborate a little bit more. How many cards would Ethan have to go through to be guaranteed to find the two if he has, let's just say you have all of your spades on the table, okay? You're guaranteed to have to look at 13 cards before you find the two at most, right? Now you could get lucky and maybe the two's at the beginning, but at absolute worst, you have to look at the first card. Oh, not the two, not the two, not the two, and so on, right? Until you get to the end. Okay, now you probably could move a little faster than that because you're not a complete moron, right? You could just sort of visually look and see, up there's the two. It's not like you guys as humans have to go, oh, is this the two? No. Is this the two? Is this the right? Like you could probably do that aspect faster. Okay. Now, that said, though, let's pretend that you're the world's stupidest human, but you're the world's stupidest human that can follow directions exactly as given. So a computer, right? Yes? Okay. So obviously, I can't just tell a computer, just look at all the cards and find the two, right? I have to actually give it some sort of procedure for that. Okay. And um, so let's actually think about what the procedure would be if I wanted to do it with that searching method. Okay. So if I wanted to do it with that searching method, and I'm assuming a computer or, really, really obedient moron, okay, because that's really what a computer uh, is doing this, then here's how that algorithm would look. Okay, I'll start with the first card. I'm looking for the two. Is this the two? No. Is this the two? No. Is this the two? Yes. Okay, I found it. Okay. Now, that only took me three attempts. It at most could have taken me six in this case because I've got six cards on the table. Okay. And then you'd move on to the three and you'd say, oh, is this the three? No. Is this the three? No. Is this the three? No. Well, yes, sorry. And move on and continue this process. Okay. Does that make sense? All right. So let me actually kind of think about Ethan's worst nightmare. Right? Would you guys agree that this arrangement of cards is Ethan's algorithm's worst nightmare? Okay? Because it takes the maximum number of attempts in order to find each card that you're looking for. Okay? So, how many tries does it take for me to get to the two? Six. And then the three? Five. And then the four? Three, two, or sorry, six, five. Yeah, counting is hard. Okay, six, five, four, three, two, one. Right. Okay. So the number of steps it took in Ethan's worst nightmare is. Let's go over to the iPad. iPad Auto and that's Professor Dunaway, by the way, is Dr. Denari. Yeah, because he teaches economics. Yeah.
currency somewhere?
Denarius was a Roman currency. Yeah. And this is also why pre-decimalization in England, they actually D was still used as a number of shillings or something. But yeah. Okay, so Ethan's worst nightmare is how many cards do we have? We had 6 cards of Mr. Sparkle's worst nightmare. Yeah, he's got to have some sparkles, right? Did you enjoy running yesterday, Mr. Sparkles? Uh-huh. Okay. Yeah. How far did you run? How much blood was involved? Only a little bit. Okay.
I would assume all his blood was involved in running.
Well, coming out of his body, right? Because I threatened that he would have to run until blood was coming out of every single orifice. Um, yeah. Okay. So Ethan's worst nightmare with 6 cards, right? The first step, how many steps did it take? 6, and then it took 5, and then it took 4, 3, and 2, and 1. Okay. Now, what is that sum? Hmm? Yeah, it is 21. Okay. Uh, now, uh, Professor Gauss, how did you get that so quickly?
6 plus 1 times 6 divided by 2.
Yes. Okay. So there's a trick for this. Okay. Now, let's say I wanted to be a real jerk and I wanted to ask you guys, or wanted you guys to add up the numbers from 1 to 100. What's the stupid way of doing that?
1 plus 2 plus 3 plus 4.
It'll work. You'll get the answer 1 plus 2 plus 3 plus 4 plus 5. The smart way to do that is to observe that 6 plus 1 is 7, and 5 plus 2 is 7, and 4 plus 3 is 7. And how many sevens do I have?
3.
3 of them, right? That's the smart way of doing it. Okay, so it took 21 operations. Now, if suppose Mr. Sparkles has N cards. Now, in our trials with the actual playing cards, N never exceeded, well, either 13 or 52, say, if you want to include all the different suits. But could theoretically we do this like if I found some card printing company and said, okay, I want you guys to print me cards and I want 10,000 of them, the number 1 through 10,000. Like I could get somebody to print me those, right? Um, okay, so let's suppose that I gave Mr. Sparks 10,000 cards in randomized order. What's sort of the worst nightmare in terms of his searching algorithm is if they happen to be sorted in reverse order, right? Okay, so if he has N cards and they're sorted in reverse order, okay, so this is the worst nightmare part of this, then how many steps is it going to take for him to find the first card? It would first take N steps for the first card, and then it would take N minus 1 steps, and then it would take N minus 2 steps, and then dot, 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 down to 1. Okay? Yes? Okay, now, let me be clear. This is assuming the worst possible scenario, which is that the cards just so happened to be sorted in reverse order, okay, from what, uh, well, yeah, just in reverse order. Okay. So this pattern, if you'll notice, let's think of our trick from before. Okay, and in fact, let me actually add in a couple of numbers here for the dot, 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 right? Let me just explicitly write the 3 plus 2 plus 1. Okay, so what's the trick here is I'm going to pair up the numbers on either end. So what's n and 1 add up to, okay, and what's n minus 1 and 2 add up to, n plus 1, and so on. And how many such pairs do I have? I have n over 2 of them, right? Because I'm pairing things up. If I have n cards and I'm pairing them up, well, how many pairs am I going to have? Okay, it'll either be n over 2 or maybe n plus 1 over 2, because, of course, it depends on whether or not I have an odd or an even number. But let me just sort of brush that little minor detail aside. I get this number, or this quantity. Okay, now can you guys see that this is in some sense really just n squared? Yeah, and that's the key. Okay, so let me multiply this thing out, right? The thing on the left. I'd get 1/2 n squared plus 1/2 n. Okay, and what I claim is that in some sense that's really just n squared for large values of n. Okay. One way to think about this, because it kind of looks like I just disappeared the 1 over 2n. And algebraically, yeah, that's sus what I just did. Okay. But think of it this way. For large values of n squared is going to be so much bigger than n that you can basically throw away the n. If, let's say you're walking down the street, you're walking over to Sparks, and you see a $100 bill laying on the ground, what are you going to do? I would hope that you would all pick it up and you would be having a really fantastic day, right? If you managed to find a $100 bill laying on the ground. Yeah? I mean, I'd probably consider that to be a very happy day. I'd buy drinks for everybody at Backstep, right? Be like, all right, tequila shots on me. Woo! Right? No? Yeah? Okay. All right, fine. But is $100 sort of a lot of money in our worlds? Yeah. Okay. I mean, it's not gonna like let you retire to some Caribbean island, right? But it you certainly aren't gonna cry over finding $100. Well, and a whole bunch of coffee, right? Or tequila shots or whatever, right? All right. Now let's say that Bill Gates goes walking down the street and he comes across that $100 bill. It's actually, he loses money if he stops to pick it up. Yeah.
Actually, he would make more on average in the amount of time it would take to pick it up, but the deals he makes are worth so much money that he doesn't actually lose money from picking it up,
Yeah.
and also he'd be more likely to pick it up and the nearest homeless person.
Well, okay, fair. Which is to say, you know, I don't know, whichever fraternity is currently on walkout, uh, right? I guess those technically are homeless people, right? But point being, is a $100 bill going to make any change whatsoever to Bill Gates' life? No. But would it make a change to your life? Okay, wouldn't be necessarily a dramatic change, but it would be a nice change, right? Okay, and so that's in some sense what I mean when the n over 2 piece doesn't matter as much as the n squared over 2 piece for large values of n. Okay, and in computer science with algorithm analysis, as we're going to continue our discussion today, we're concerned with large values of n, right? Sorting is not particularly interesting with only 3 cards, okay? And it's not particularly hard either. It's when you have 3,000 that suddenly you have to be a lot more cognizant as to how the hell you're doing it so that you're as efficient as possible. Okay. All right. So the Sparkles algorithm, we'll call it that, okay, is a searching algorithm. It's just a linear searching algorithm, and it basically, at worst, can take n squared or roughly n squared operations. Okay. Now, let me show you a genuine sorting algorithm, and we'll argue why that actually is going to take basically n squared also. Yeah. Okay. Yes. The over 2 actually doesn't matter in some sense. And I'll make precise what I mean there later. Okay. With the mathematical definition.
Does it matter for how the number of steps grows?
Right. And that's what's critical here, right? If the number of steps grows by 1/2 n squared, it's still growing with a quadratic curve, and it's the quadratic part that we want to concentrate on. The constant out front is sort of slop. Okay. Okay. So that was an algorithm to do it, which was basically to change the problem from one kind to another. Let's suppose instead we actually tried to sort them. Okay, so let me shuffle them just for the demonstration of this algorithm, and then we'll kind of do the same sort of thing. Oh, actually, before I do that, what's the best case scenario for Ethan's algorithm? Yeah, what would happen if the cards just so happen to be in order? How many operations would it take? It would take, you would have to check each card, so it would take n operations if he had n cards, right? Because he has to say, is this first one the 2? Hey, look, it is. Is the second one, the next one the 3, and so on. Okay, so at best, it would take n steps, and at worst, it would take n squared steps. And you guys could guess, what about on average, what would it take? It's going to be n squared, basically. Now, it might be not quite as big as n squared over 2. Maybe it's n squared over 4. I don't know, right? But point being, if I had told you guys to sort this way and collected all the data, and then I did the min, max, and average curve fits, I would probably see n squareds at least for the average and for the max. Maybe not for the min, because maybe somebody would get lucky. But on average of the minimums, yes. Okay. All right. So yeah, in algorithm analysis, sort of what we want to think about is what's the best case and what's the worst case, and maybe in some sense by running the algorithm a whole bunch of times, we could come up with some sort of average. Okay, and think of, all right, in the real world, your data probably isn't going to come perfectly sorted or perfectly anti-sorted. It's going to be jumbled up, but not perfectly jumbled up, right? So on average, what's it going to take? All right, so let's take the cards, and okay, well, I did kind of a crappy job here, but whatever. Okay, so we're going to look at a sorting algorithm called the bubble sort method. Now, there are a lot of different sorting algorithms. Bubble sort is, in some sense, the worst algorithm because of its how many steps it takes at worst, but it's the easiest to explain. The other algorithms are much harder to explain, but can be more efficient in general. Okay, so here's how bubble sort works. I'm going to take the first pair, okay? Are they in the correct order?
Yeah.
Yes. The first card in the pair is smaller than the second card in the pair. So I'm going to move on to the next pair. Are they in order? Yes. Okay. Then I'm going to move to the third pair. Are they in order? Yes. Okay. Then I'm going to move to this pair. Are they in order? No. So I'm going to swap them and move on to the next pair. Are these in order? No. So I'm going to swap them. Okay. Now, the net effect of that is on the first pass through these things, where has the biggest card ended up? At the end. Okay. So on the next pass, how many cards do I have to examine? Not 6, but rather 5. Okay. So I've got the 7. He sort of bubbled his way up all the way to the end. And now I'm going to repeat the procedure. And the big cards are going to bubble their way that way. And the little cards are going to bubble their way this way. Yeah.
Couldn't you only look at the last pair still there that was in order first? Like, not look at the majority of the pairs at the beginning that were in order?
But how did I know that they were in order?
Because you already just checked them. So like for the next
Oh, I
pair.
see what you mean. Yeah. Yes, we could modify the algorithm to kind of speed it up a little bit, but um, the thing is, like, I got lucky, right? In the sense that I could have ended up with the 4, the 6, and the 8. They're still in order, but I'm not done yet, right? And so the fact that I just so happened to get a consecutive run here was luck, um, and that wouldn't work, right? Like from a computer perspective, like how do I know that I really already have them in order, fully in order? I don't. All I know is this is less than this and this is less than this. So they're in a partial order, but they're not necessarily, I'm not done yet. Okay. All right. So repeat the procedure. Are these, is 4 less than 5? Move on. Is 5 less than 6? Move on. Is 6 less than 2? No. Swap. Move on. Is 6 less than 3? No. Move on. And the 6 has now bubbled its way to the final position for it. Okay? Continue. 4 and 5, are they in correct order? Yes. 5 and 2? No. Swap. 5 and 3? No. Swap. Okay? I can stop and go back to the beginning. 4 and 2? Swap. 4 and 3? Swap. Okay. 2 and 3. So I finished that set. 2 and 3. Okay, so I didn't need to do a swap there, right? That is the bubble sort algorithm. You basically start pairwise from the left to the right. Okay, we could have done this right to left, okay, but we just have to pick something. Okay, so I'll just go left to right. Okay, and I'm going to examine each pair and do a swap if necessary. Now, strictly speaking, uh, even if I don't swap, have I done work? Okay, what is that work? Checking, right? So in this algorithm, right, or really in Ethan's, there's really two kinds of, or for, say for this bubble sort algorithm, there's really two kinds of things that I'm doing. Okay, I have some swap operations. Well, that takes some work. And I have some check operations, and that also takes some work. Okay, and if we want to keep track of the sort of total amount of work that one has to do here, we really need to count both the swaps and the checks. Okay, because you might still do a check to realize that you don't need to swap. Well, then you don't do the swap, but you've still done a check operation. Okay, so we'll count those in some sense and do, figure out basically how many operations does it take. Okay, so does that kind of make sense for how the algorithm works, or this particular algorithm? Okay, now in Ethan's algorithm, in some sense, there's not a swap operation, but we could call this operation picking up the card and putting it on the stack of sorted cards, right? So you go through, you find the two, and what do you do with that? You take it out of the pile and you put it in uh, the sorted stack, right? And then you return to what's left. Okay, that action of in a computer sense, right? That's like moving data from one place to another. Well, that's still a step, right? Um, but even if we just counted the number of checks, not counting the data moving, the number of checks for that searching algorithm is how many at worst. If there are n cards, it's essentially n squared. Okay, and well, okay, sorry, it's n checks for the first card. How many for the second card? N minus one. How many for the third card? N minus two. Dot dot dot. How many for the last card? One. Okay, which okay, one, whatever. Right? But that's exactly the pattern that we saw a minute ago when I was writing on the iPad. Right? Okay, so let's go back to the iPad for a moment and let me write this another way. Okay, so let's be smart and let's write this in a different way. Now, in math, we have a notation for this. Okay, this is the sum of the integers I from 1 to n. Okay, so let's think back to high school. What's that big letter? That's a sigma. Come on, Brad. Let's strap you to the chair. We're going to waterboard you too. Yeah. I've got plenty of water, and I'm sure we can find a towel, right? Uh, okay, so what does this sigma mean? Sigma means to add, okay? And what am I adding? I'm adding a number, and that number starts, so every time I add, I'm going to add this formula with the number I plugged in. The starting value of I is 1. The stopping value of I is n. Okay, so what this means is to do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus dot 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 plus n. Well, isn't that the same as what's in the orange box? Except it's written in reverse order. Okay, but it's the same thing algebraically. And can I just reverse the order? Like algebraically, does it matter what order I actually add in? Because I'm adding up finitely many things, right? That could be a very large number of finitely many things, but do I have a finite number of things? Yes. Okay. By the way, how many of you are in Calc 2 or might contemplate taking Calc 2? Yeah. Are you in Calc 2 now? Have you guys started talking about infinite series? Well, guess what? You can't always reorder the terms of an infinite series. Sometimes you can, sometimes you can't. And when you can, it's called absolute convergence. Okay. Yeah. And when you can't, it's called conditional convergence. Okay. Yeah.
I've seen one such series, different values based on the order of value.
Yes. In fact, it's worse. Okay. Pick a number.
52.
Pick your favorite conditionally convergent series. Okay, that might take him a little longer to choose one, right? But I can find a rearrangement of his conditionally convergent series that adds up to 52, right? Doesn't matter what number you pick, right? Huh? Yep. I, there's a procedure for doing it. Yeah. So you can't reorder infinitely many terms, right? So for those of you guys who take some calculus, think of this as a preview of coming attractions for Calc 2. Okay. All right. Now, for our case, though, we don't have to worry about any funny business because we're working in a finite world. This is the thing that we basically were adding up, right? And in this, we got this by in our case the Sparkles algorithm, right? Which was just look through all the cards until you find the 2, and then the 3, and then the 4, and so on. Okay. Well, what we've just discovered is that this is actually equal to that formula. Okay, which we've said is in some sense basically n squared. Okay, now I'll elaborate on Friday as to what I mean by the in some sense, right? I want to make that precise. For right now, I'll just write sort of a little squiggle there. Okay. Um, okay, how many of you guys ever saw this formula in high school? Yeah? Okay. Um, how many of you probably saw it but forgot about it? Okay. Now, here's sort of a fun question. How do I know that, like, I'm adding up whole numbers here, right? So the sum better be a whole number. How do I know that this is always a whole number? Anybody but Thomas? See if anybody can see it. Other than it is, in fact, right? Well, what kind of number is n? N is an integer, correct? So either one of two things is true. Either n is even, in which case n over 2 is a whole number, or n plus 1 is even, in which case n plus 1 over 2 is the whole number, right? So no matter what, whether n is odd or even, I know that this quantity is always going to be an integer. Well, it damn well had better be, because how did I get it? By adding up a whole bunch of integers. And how often has it happened when you add up a whole bunch of numbers that are whole numbers and you get something with a decimal point? It better not happen, right? If you pizza when you should have French fried, you're going to have bad time. Okay. All right. Let me just finish with one thing here. And we'll kind of we'll continue with this next time. So let me just make a mathematical definition and we'll return to it next time. Okay, so a function f of n is said to be big O of g of n. Okay, so big O of that thing means that there's a constant so that for all n, f of n is always less than or equal to that constant times g of n. Okay, so let's just make that definition and how that enters into our discussion. Maybe you can start to see, okay, this is the way in which I'm going to make this squiggly or this squiggle sign a bit more precise. Okay. Okay. The other thing I need to do is, did I post the study sheet to Canvas for the exam? I did actually do it. Okay. I woke up this morning and was like, crap, did I post that or not? Okay. So the procedure for that on Friday, okay, when I walk into the building at 8 in the morning, well, just shy of 8, I'm going to put a stack of things outside my door. Now, are you any of you guys going to go out there at 8 and go do it? No, because your butts are going to be here in class, right, while we're doing other things. The other guys can take it at 8, but what are the odds do you think the guys in the 11 o'clock class are going to wake up extra early to take it? Probably not very high, right? Okay, so grab the exam, go find a quiet place to work for about an hour, bring it back and have it back there by the end of like 1600 on Friday. Okay. Now, those of you who are on football and you're leaving at whenever, right? You don't have class in a solid block from 8 to noon, do you? None of you do. Okay. So none of you football players are going to be like, oh, we could possibly do this. Looking at you, Mr. Sparkles. Okay. Mr. Zapata. Yeah. Okay. All right. So we got the procedure. Now, when you do the exam, other than maybe some scratch paper, you don't need and should not have anything else. And do yourself a favor and silence your cell phone and, so on, right? So that you're not disturbed during it. Okay? Gucci? Well, you're going to be disturbed, yes, but that's a different problem. So, all right, I will see you guys on Friday. Have a good one.